Good. With the terminology set, let's have a look at a few proof templates. And these go step by step through different kinds of statements. Any statement has a different template that you can apply, or a set of templates. The most interesting type of statement is the implication, just because it pops up in different other statements, and it's just the most commonly found one. So if we try to prove A implies B, we can't just try a direct proof. We start from A. Remember, a proof is axioms and inference and statements derived by inference rules from previous statements. If we prove an implication, we start with the axioms and A. That's also something we can start from. And so a direct proof would try to derive B by following through these steps, starting from A and the axioms. That's the obvious thing to do, but you can also do slightly different things. You can reformulate the statement first. If you go back to this equivalence, then you find that A implies B is logically exactly the same as not B implies not A. And sometimes it's more convenient to do such an indirect proof, or fancily called proof by contraposition, because you swap these two things around. Before, I could start with A and try to prove B. Now I can kind of go from B to A, but I have to negate things. So I start with the negation of what I want to prove and try to show the negation of what I start with. So we could try, we'll see examples later. Slightly related, but a little different in the way you carry out things, is a proof by contradiction. So you assume that the statement you're trying to prove is not true. And that comes down to assuming that A is true, but B is not true. So if A were true and the implication is true, then that would imply B. So we're assuming something that we don't believe. And then you try to derive a contradiction from that. So you try to arrive at a point where you have, I don't know, x equals 5 is one thing, but you could also show x equals 7. And so these two things contradict each other, which means one of the premises must have been wrong. That's another way to show implications. It's often, well, maybe this is something about human nature. I don't know. It's often easier to find contradictions than direct proofs. I don't know. Yep.
So, proving by contradiction, like, if an implication is true unless you have a true statement implying a false statement. A implies B is true unless A is true and B is false.
Sure.
So if you want to prove a statement S is by contradiction, you can assume not S, that not S is true, and show that not S implies something that is false. So if not S, if a true statement implies a false statement, the implication is false. So you know that if not S implies false, you know that something is false, so that unequivocally false, like X and not X, or
sure.
0. You know something that is false always, and you know since the left-hand side, the right-hand side is false, and the implication is also false, then the left-hand side must be false. Because false implies false is valid, but true implies false is wrong.
Yeah, exactly. Okay, so I mean, to summarize this a bit unfairly, you can apply proof by contradictions to all kinds of statements by just negating what you try to prove and try to arrive at the contradiction. It's just for implications, usually, it's maybe less obvious and often effective. Yeah, let's try to get through some of these things, because there's a few things I want to touch on later. Another thing that's very versatile and often helpful is to distinguish cases. It just happens that sometimes it's easier to make your problem harder. Instead of doing one proof, you do two, but each of them is easier. So you have some other condition C, and you can have A and C, or you can have A and not C. Those two together are everything you can have with A. But sometimes the arguments get easier if you have additional ammunition. I'm sure we'll find some examples later in the module for this. The important bit here is that it has to be an exhaustive case distinction. You have to cover all possibilities. That looks super obvious when I write it like this in terms of these logical formulas. It's much easier to lose some case when you're folding this up into a big proof. So it can help to spell out explicitly. I'm looking at, let's do a case distinction. I'm looking at this case now, and there should be a last case, everything else. Then you have covered everything. Let's do another quick example just to see if this made sense to you guys. Oh, come on. So you take your time, I'll just start writing some things. All right, I think we have. Is anyone still voting? Can I lock it? Never mind. I mean, you can cheat and change your answer, but you don't gain anything from it. So it's an indirect proof if we do this. Come back to it. I thought it's helpful to actually do the full proof, just to show you a quick example. So it's not a super important statement for algorithms, but well. So if n is odd, that means we can write n as 2 times k plus 1 for some natural number k. That's the definition of odd at the end of the day, and depending how you formulate it. So this n0 is just the natural numbers 0, 1, 2, and so on. And then if we have that knowledge about n, we can have a look at what n squared looks like. And then that's just a little bit of algebra, arithmetic, depending how you want to phrase it. And we arrive at something where n squared has the same form. So that's some number k prime. The important bit about this is that k prime is 2k squared plus 2k. If k is an integer, then this k prime will also be an integer. We're just doing operations that stay in the integers. So that one, again, is a natural number. And that implies n squared is odd, because we've written the number in the shape that is required for odd numbers to exist. 2 times something plus 1, right? Apart from the usual type of miscalculations when I do this on the spot. That's the proof that is meant in this question. And if we want to highlight why this is an indirect proof, we can split up the individual parts. So that's our statement A. That's the statement B. Now we showed n is odd implies n squared is odd. That's the same as not B. It's just slightly hidden because I changed from odd to even. But for integers, any integer is either odd or even. So not even means odd. As odd as it sounds. And that's not A. Right? So we showed the implication not B implies not A, and that's an indirect proof. Questions so far? That's what I mean by templates, right? You start with a statement like this, and maybe it's obvious for you if you think about a few examples. Writing down a rigorous proof is actually quite challenging, even for these very simple ones, or maybe exactly for these simple ones. And having the right proof templates at hand, you can just go through them, and often one of them is applicable. And here, this turned the task into a simple computation, because we could take the knowledge, n is odd, get some tangible thing out of it, write it as 2k plus 1, and then do something with that knowledge. Other types of statements that we will often meet are these, and these will be, I'll go through these quicker because they're usually falling back to what we already know. If we want to prove that A, if and only if B, is equivalence, we know that that's actually just two implications. So it means we have to prove two implications separately. And most of the time, that's the easiest way to go about it. It makes the proof twice as long, maybe, at least logically, but usually it's much easier to prove an implication than to directly prove an equivalence. So whenever you see an equivalence and you're asked to prove it, your automatism should click in and say, okay, I have to do these two things, prove two implications instead. Apart from combinations of logical statements, we'll often talk about sets and other kinds of mathematical objects that reduce to sets at the end of the day. And one of the simplest is we can have a set of some objects S and another set, and we may want to prove that R is a subset of S, right? You know this symbol, I hope. That's the subset relation. It means every element in R is also in S. You can rephrase that as an implication. If you want to be picky, we should have a 4x for all x in front of this. We'll talk about these weird quantifiers in a second. So you can rephrase a statement about sets as an implication, and we know how to deal with implications, don't we? We can also sometimes want to prove that two sets are equal, but S equals R is the same as S is contained in R and R is contained in S. So again, we can go back to implications all the way through, and we know how to deal with those. That's my assumption for now.